Hello, students, into section 11.3. Got some questions from one of you, so I'm going to go through those. We're going to start with, see here, 8, 14, and 19. So let's take a look at those. We'll jump down to question 8. Okay. So in part A, prove that the lines are parallel. And in part B and C, solve for X if you know that the lines are parallel. Okay, so the question says, can you walk us through an accurate proof for parallel lines? What are you looking for? Also for B and C, how do you solve for X when it's placed where it is? Okay, so let's see here. So all of these are using the same theorems from this chapter. Let's see here. And they start with the parallel lines component. And so it's theorem 11.2. And the big piece about this theorem says, if any two distinct coplanar lines are cut by a transversal, and that's kind of the picture you see up here, then, so we have this kind of overall distinction. So first off, before we even get to our actual statement, which is a pair of corresponding alternate interior or alternate exterior angles are congruent. See, this one's an if and only if statement. But we can't get to that until we meet the conditions. So the big piece we have to do before we really start looking at any of these problems is we have to have two lines cut by a transversal. Now, again, when you draw your lines, they may not look parallel. They may even look less parallel than that. The picture may look less parallel. The pictures are not drawn to scale. Again, most of the time they can just be a quick sketch. The line could look like this, so it mirrors very closely what you see in the book. The line could look like this. The transversal does not have to have a particular direction. Okay. Also, you could think of lines looking something like this, and the transversal is horizontal. So this is line 1 and line 2, and then my transversal is line L. So again, you just need two lines cut by a transversal. Transverse, kind of going across them, would be transversing or transversal. Okay, so that's the idea. So if you have this picture, that's what it says. If any two are cut by a transversal. So we realize we don't go any further with these, with this theorem, unless that is met. You have to meet the condition. So you're like, well, I have one line and it's cut by another. Awesome. That is not this theorem. This theorem does not relate to that whatsoever. Okay. Okay. So now we have that. Then now here comes a pair of corresponding angles, alternate interior or alternate exterior, are congruent if and only if the lines are parallel. Remember, if and only if is a big thing, right? IFF. So if the corresponding angles are congruent, then the lines are parallel. What would that look like? Over here, what you would say is I need a pair of angles that are either corresponding alternate interior or alternate exterior. So alternate exterior would be this angle would match up with that angle. Those are alternate exterior angles. If you are able to prove that those two angles are congruent, then line 1 is parallel to line 2 because of this theorem. Okay. What else could it be? Doesn't have to be those two. It could be alternate interior angles. So again, those would also be fine. So if you prove these two angles are exactly the same, then the lines are parallel. And finally, you have corresponding angles. So that would be angles like this and that. And again, there's multiple pairs of corresponding. You can go back, either watch my video or flip back a few pages in the book and you'll get all those definitions. And there they are. If these two are congruent, then the lines are parallel. But that is not just an if-then statement. It's if and only if. So if I tell you that line 1 is parallel to line 2, then we go the other direction now, which is really great, because what it means is that corresponding angles are going to be congruent. Yep. And if we needed it, alternate interior angles are going to be congruent if we know they're parallel, because that's what it says. And, right, alternate exterior angles are going to be congruent. So if you know it's parallel, you get all of these other things for free. So that's what we're starting with. That's the theorem that we have. This is such an amazing tool. Yes, we will be using it an awful lot. Okay. Well, so let's take a look. So here's this one again. I don't know if I want to necessarily just do this particular problem. I could do one that's similar. This problem again is one that actually ties into a separate theorem. So I'm not sure if I want to do this entire one, but let me take a look. Let's get a little bit of white space and maybe I'll just create something here. Okay. Oh, maybe I'll go to part A. That could be good. Let me go to part A. Okay. Part A, question 8. Okay. So here we go. These are very similar. If you look at A, B, C, D, E, F, right? And these say determine whether they are parallel lines. Okay, whether they are parallel lines means you have to meet one of those pieces. So I don't know they're parallel lines. By the theorem we just talked about, I need either corresponding, alternate interior, or alternate exterior. Those are what I need. I need one of those. So when you look at any one of these problems, you're trying to see. Sometimes you can spot it right off the bat. For instance, right here. By definition, these angles are alternate exterior angles, and they are congruent because they have the same measure. So I could conclude by theorem 11.2, the two lines are parallel. Yep. Okay. I could do something similar here in D. Let me change color just so we don't think it's the same thing over and over again. Here I have a right angle and I have a right angle. Look at where they're located. Those are corresponding angles, and they are the same measure, which means they are congruent. If you have congruent corresponding angles, then M is parallel to N. A might be one of the more, I guess, a little bit trickier, but that's because you have a 130-degree angle and you have a 50-degree angle. So what you could do is say, wait a minute, line L is a transversal. So I actually know the angle right next to the 130 has to be 50 degrees because it is supplementary. They make a straight line. So if I know one of them's 130, the other has to be 50. And then you could say, well, wait a minute, but this other angle down here is 50 degrees, and those are alternate interior angles. So M is parallel to N. Okay. So what we're showing now, and in this case, so far, all three of those have been congruent angles and therefore parallel lines. If this wasn't 130, like on an exam, if I said this is 120, then the angle next to it would be 60 degrees. The corresponding is not congruent. So the corresponding angle of 60 degrees doesn't match with the 50-degree alternate interior, so therefore not congruent. So again, this congruent is a two-way street to M is parallel to N. And that also means, remember the biconditional from chapter 2. If this is false, then the lines are not parallel. So if it works, they're parallel. If it doesn't work, they're not parallel. So we actually have a very, very strong statement here related to these. And likewise, if you look down here, you got this beautiful picture here, but you could do the same thing. This one is my hint, I guess, for the one in part B, because you could just look and say, well, that's 110, then this angle up here, what is this angle going to be? And use what you know about lines to form that angle. Or come over here and form this angle right here. That's fine. Or use it to form the angle down here. Pick an angle and then use it to find that piece. And I think you'll be able to solve for either saying it is parallel or is not. All right. Let's see here. So there's A. I think in B had a slight difference, right? Because yeah, these are the ones where things get a little crazier. And so I think I did give a nudge on one of the videos to show a lot of different approaches to this. Remember, if you want to talk about parallel lines, you need to have some of those angles created. In order to create those angles, you need two lines with a transversal. That's why I emphasized at the beginning of this video, I said your picture has to look like this or something like that. Two lines cut by a transversal. Okay, so look at this picture. You don't have that, right? So what you do have is the power I hereby give you the power to create or to extend lines if you want to. And now you do have two lines cut by a transversal. Okay. All right. So now what good is that? Well, now you also built a triangle, and we know something about triangles. Okay, if you don't like that one, that's fine. Maybe you extend this line down, right? And you extend this line over because lines are infinite. And you could say, okay, now I know something else. So now I would have, you know, this line here would have to match up with that angle there because the lines are parallel and because I have two lines cut by a transversal. So that's the idea for these problems. Are there other approaches? And the answer is absolutely there are other approaches. These are just two of them. So if you were to, like, you could draw a line here, making a new transversal, right? That just goes through those two vertices. And then you know something about, because of the prior theorem, you know something about this total angle and this total angle, and how I'll just call this big one angle B A and this one angle B, and how you know that angle A plus angle B has to equal 180 degrees because the lines are parallel. You could use that to determine what these other angles would be. Also, you have a beautiful triangle here. A beautiful triangle, right? And so there is a nice little theorem as well about a triangle and the other angles that would align with that triangle. So that is another piece you could do. So you could use a triangle argument. You could use this almost vertical one type of argument. What else have I seen? There's a lot of arguments you could make. And that's, I think, the beauty of geometry. You could use this point and go, I'm going to create a perpendicular line straight down. And because the lines are parallel, then these have to be both perpendicular. That is not the case over here before, what I had before. This line that I drew between these, I don't know if it's perpendicular. It may look perpendicular, but it doesn't have to be. Okay, so we got to be careful with that. So these are both 90 because the lines are parallel. And then maybe I could create something. If I know this angle down here is 90 degrees, I bet I could figure out the missing piece here. I bet I could figure out the missing piece there. Again, so that's five different ways that you could go about proving this. So yeah, a lot of options, and pretty similar with the other one, the one right below it in part C. Okay. All right, so there we go with problem 8. And let's see here, 14. I said 14C. 14C. Okay. All right, so 14C. Well, let's see here. We have a shape. So make sure, what kind of a shape is it? Okay, so let's create a similar problem. All right. We have to create a similar problem. So let's do one that is I don't know, something like this, right? Okay, so here's the smallest angle, next smallest, so smallest, next smallest, next, whatever. So let's just say that this is my X, Y, Z, and W. Okay, and I'm going to tell you it's an arithmetic sequence, and I'm going to tell you that one of these angles is, let's say, I'll tell you Y is 88 degrees. There you go. Okay. But I also told you, even though one of them is 88 degrees, the others form a nice arithmetic sequence. So put them in order. X, Y, Z, W. Put them down what you know. I know only this one is 88. Awesome. But here comes the fun. Remember what we've already done with arithmetic sequences. You just don't know the common difference. So we'll just say, I don't know the common difference. Then add and subtract. If you need to go backwards, you can subtract. You need to go forward, you can add. And then you'll have this sequence where, in effect, you do know all of the values if you knew what D is. And then you can just say, well, wait a minute, this is a quadrilateral. You know, how many degrees total? Total interior angle sum equals question mark. Okay, we know for a triangle it's 180. I forget what it is for a quadrilateral. And I forget what it is for this one. 1, 2, 3, 4, 5, 6. Well, that's 6. Man, I've totally forgotten. If only there was a way that we knew how to do that. We will also build that coming up in class. Depending on when you watch the video, we may have already built it. So we will have a nice formula for that. Okay, so that's how we can get that sum and then use it. So just add these up and you've got something really nice. And what's great, and some of you saw this before when we did one of those like adding up 3 consecutive numbers, you realized, and what I loved is some of you were like, hey, I'm starting from the middle one, because if I use the middle one, I can go up and down, and those go away when I add it all together. So really, you end up with a beautiful and quick way to do that. All right. So there we go. So there's 18. Yeah, and your common difference, let's see here. Your common difference doesn't have to be a nice number. As a matter of fact, if you just make a problem up, most likely it's not going to be a nice number, right? So the one that I was working on, or the one that I just had on screen, would have been, what, 88 times 4 plus 2d is equal to 360 degrees. So yeah, it may have fractions or decimals. Yeah. And if you have to choose between those, uh, I'm going to say use your judgment, right? You have a choice. If the answer is 2/7, right, then you can choose to leave it as 2/7, or you could have chosen the decimal form, 285714. You just have to put the bar over it because those are equal. And because those are equal, the power of this is you get to choose which one you like better. Okay, so if you have 3/4, you could leave it this way, or you could write it this way. It does not matter to me. It shouldn't matter to you. And you should be comfortable enough to do both. But yeah, if you get a decimal, that's fine. Just be aware, if you do get a decimal like 0.3 repeating, that is not the same as 0.33. Okay. The one on the right is rounded. So once you round enough off, it may not be the same as what it was previously. Let's take a look. 19 is the next one up. So here we go to the next page. Question number 19. Okay. What kind of a quadrilateral is ABCD? Actually, this ties into one of the previous questions, so it's a good one. It's very fitting. So let's take a look. So when you see this, you always look at these and say, okay, well, I see line segments. What you may be missing is by doing something like this, you could say, wait a minute. I actually have 2 lines being cut by a transversal. And you have that throughout this picture, right? Each one of the sides could be serving as a transversal. There is another transversal right here. So now that you know this, think about what you know about this angle measure. And I'm sure some of you are like, I really wish I knew what they were. I don't know what they are, but I also know that since I don't know what they are, I could call them something. So that if I looked here and I said, okay, I'm going to call this angle X, the measure of that is X. And the other angle I will call Y. Then we know something. We know X plus Y plus X plus Y is equal to some number. I'm going to make sure you have to know that number. I'm not going to give you that. And then, of course, you could condense this down to say 2x plus 2y is equal to that number. And now if you do simplify, you will not be able to solve for x or y in this picture. I know you want to, but that's okay because we could actually simplify, divide everything by 2, and you might get x plus y equals some new thing over here when you divide by 2. And that tells you something because you have x and y together right here. Okay, right there. So my hint is use something like what I've shown here and then connect it to the theorems that we've talked about in this section. And then you should be able to tell something about this figure. And a pretty big hint. One of the biggest things, if not the biggest thing we did in this chapter was talk about parallel lines. So that would be my big nudge on that. I would say be careful It's tempting to say that the opposite sides have to be congruent. We don't know that. It's tempting because you want to, maybe because from a former class, but everything in this course you have to be able to justify. And you could say, oh, these are opposite sides are congruent. And I will simply ask you why. Why do you know that they're congruent? Well, they have to be. That's not a good enough answer. It isn't. Okay, because then it becomes just a memorization. Everything that you think you have to memorize has come from something that you could understand or know. And that's the goal of this class. So take that as my nudge in the right direction there. All right, let's take a look at the MCs. There were a couple of these. MC number 6. Oops, I missed it by one page. Scroll to the bottom. Question 6. Oh yeah, how to find the sum of the measures of the interior angles of any convex pentagon by choosing any point in the interior and constructing the triangles as shown. So you need to tell someone how they can do that. How can I use this to find the total number of angles? Well, at this point, you should have a few things under your belt. So you should know interior angle sum of a triangle. Like that is something at this stage where you should be like, yep, I got it. I know it. I use it. I'm good. And then take a look at the picture that they've drawn. They put a point in the middle and they drew lines out to each of the vertex. There they are. What did you just create? You created a triangle number 1, triangle number 2, triangle number 3, triangle number 4, triangle number 5. Well, if you know the interior angle sum of the triangles, you know all of the angles that have been summed up. So that would be this little angle here, this little angle here, and this one up top for triangle number 1. 3 different angles got added up to give you triangle 1. And that's, you know what that sum is. Repeat the process for number 2, repeat for number 3. At the end of the day, what you're trying to find, and again, this may be the part where there's a little bit of confusion. What is your goal? What am I trying to do? You're trying to find the sum of all, and I'm just going to trace over these and then try to drag them just a little bit so that you don't see these other lines. Let's see how well it works. Okay. There we go. Well, that's what we get. Okay, yeah, that looked, sure looked a whole lot better when it was right on top of something else. Okay, there we go. So point there and then straight here. Okay, that's horrible. I will try to find the straight line tool so that I don't look quite so, like it doesn't look quite so bad. Okay, here we go. Okay, maybe that looks better. Please look better, please. Oh, wow. Okay, wow. That was crazy. No. Okay, here we go. Please, please, please. There we go. Okay. What are you trying to find in this problem? It says you're trying to find the sum. This is where you want to do the reading and the highlighting. If you have a highlighter, bring it. If you don't have a highlighter, get a highlighter so that you can bring it. What are we trying to do? How to find the sum of the measures of the interior angles of any convex pentagon. That is what you're trying to do. You're trying to tell a student how to do that. Then they tell you, here's the process we want you to use. But remember your goal. What am I trying to do? Oops, still in highlighter. I'll get better. What am I trying to do? I am trying to find the sum of the interior angles of a convex pentagon. That is adding all of the things that I've indicated in red, only those things. And if you come over to this shape, you should be able to say, well, wait a minute, I actually am adding some extra things in there. So that the answer might be too big. Good. If it's too big by how much? And why is that too big? Now, this is in contrast to the other technique that they gave for doing a convex pentagon, which was to draw diagonals. What you have in that picture to my right, this one over here, is not diagonals. Diagonals would look like this. And in this case, I end up with 3 triangles, not 5 triangles. So use that as part of your explanation. Okay, let's see here. Number 6, number 8. Explain how to find the sum of the measures of the marked interior angles like the following. Okay, how do I find the sum of those? There you go. You can choose any method you want as your explanation, but the one that we just did on the previous problem is perfectly fine. You could create a point in the interior like this, and then create triangles, realizing you might be overcounting a bit, but just make sure you remove that, and that will tell you how to find the sum of the interior angles of this particular shape. The point in the middle option. What else could you do? You could create diagonals. In this case, you probably only need one diagonal to create some triangles. That's fine. Okay. What else could someone do? Well, I guess you could come out here and say, okay, I could create this and that and pretend that I have A, B, D as a triangle. And what would happen if I built a triangle in the middle of it? But just remember, you need to remove this from the outside edge because it shouldn't be counted in at the end of the day. So that's a third way. So 3 different ways that you could go about doing this. Okay, conjecture whether the theorem for the sum of the measures of interior angles of a convex polygon is true for concave polygons. That is you telling me, Scott, I actually think the formula is the same. Or, Scott, I looked at this example and I know it's different now. So now I believe the formula is blank. And then you have to justify your conjecture for pentagons and hexagons and explain why it's true in general. You're explaining why, you're not justifying why. So why would it be true for an n-gon? And that's what it means when it says in general. It's not a, this up here would be like a 4-gon, which is a quadrilateral. They ask you to do it for pentagons, which you can think of as 5-gons. And for hexagons would be like a 6-gon. They're saying do it in general. So in general would be an n-gon. All right. That takes care of those pieces. Let's jump over here. Number 8. And number 10 is the last one. So number 10. Oh, look at this. Yeah, this is, again, a bunch of transversals right here. Let me see if I can zoom in a little bit. Okay. And then A and B are cut by transversals C and D. All right. If measure of angle 1 equals measure of angle 3, and measure of angle 2 equals, I would probably color code these. I get a little lost when they use the same symbols over and over again. So like I would say, okay, so they say angle 1 is the same as angle 3. Okay, got it? And then angle 2 right up here is the same as angle 4. Okay, so blues are the same, reds are the same. Okay, that makes sense. And perhaps because you have a couple things, you have lines cutting across, but you also have a polygon. And if you have a polygon, you could find the sum of the interior angles. And that right there would be a very quick way to be able to kind of move towards the direction showing it that these are parallel if they are. Can you conclude that they are parallel? What a great question. When it says justify your answer, the expectation is that you can provide justification. Tell me why you think that they are parallel. Okay. Now, if you get kind of hung up for a while and you're saying, hey, but there's so much going on in this picture, awesome. Then why don't you come along and just temporarily say, I'm going to ignore line D just for a moment, right? You build the quadrilateral, do something with it, but then just say, you know what, I don't want to look at these other pieces. All right, so erase them, draw it. Here's your 2 lines being cut by a transversal. There it is. Okay, we're trying to conclude the lines are parallel. That means I don't know that they're parallel. So now what do I know about 1 and 2 that might help me to decide whether the lines are parallel? And I'll cut that and delete it. So it comes back, but you feel free, erase it. If it bothers you, cover it up with your finger. If you've already got it drawn, like just cover it up with your hand or a pencil or something and say like, okay, ignore that one for a moment. Let me just focus on line C. Okay. All right. There you go. Did that get you going in the right direction? You got this. I'm not going to say that it's necessarily easy, but keep looking. When they provide you with a theorem, it's like a guidebook. It tells you, what do I need to be looking for in order to conclude this thing? If you meet the condition of a theorem, then the conclusion has to be true. And that's why if we know lines are parallel, that'd be like the condition, then I know alternate interior angles are congruent, or I know corresponding angles are congruent. So I get that for free because that's how the statements work. All right. Hopefully that helps. Off you go.